All right, folks, so today we're going to cover what is, frankly, a lot of review from grade 11, but we're going to be putting a spin with radians on them here. Radians, obviously, that we just learned in lesson 6.1. Now, we'll work here with a review of some terminology, then we'll go over a review of some strategies to interpret, to calculate, to evaluate trigonometric ratios of some special angles. Now, first we'll work with an angle in standard position. So an angle is in standard position if it has one point at the origin, really. If your terminal arm, and that's here in orange, if it starts at the origin and it heads obviously outwards, and we measure our angle if it's in standard position, we measure our angle from the positive x-axis, which is here on the right-hand side, counterclockwise around. So here we could write theta. That could be our angle in standard position. Our angle theta is the principal angle, and that is it's a positive angle in between 0 and 2 pi. Remember, 2 pi is a full way around a circle. That's 2 pi. So our angle theta, as we have it currently sketched, is the principal angle. Now, we also could measure a principal angle. It would satisfy this. We could also measure an angle in standard position. It would satisfy this if we measured our angle still from the positive x-axis, if we went around a full time and then we stopped at this terminal arm. So notice if we're working here in standard position, then a positive angle will go in this counterclockwise direction. All right, a counterclockwise direction. Now, and this next bit is whereas, frankly, where some folks can get confused. Where we're working here, whoops, just trying to, there we go, get rid of that dot, is the related acute angle. So the related acute angle is an acute angle, and if it's acute, that means it's less than what we used to call 90 degrees, so it's less than pi over 2. And that means it's going to be less than this angle. Less than this angle. These are all pi over 2 in size. Okay, so our related acute angle is always going to be measured from our terminal arm to the closest x-axis. All right, so our related acute angle in here would be this. Our related acute angle is given by the Greek letter alpha. Now, we need to be careful. A common mistake when coming up with your related acute angles would be to put your related acute angle in between the terminal arm and the y-axis. That's not where it goes. The related acute angle is always measured against the x-axis. All right, now this is an always positive angle, and that means what we're measuring with this angle is the difference between our terminal arm and the closest x-axis. So anytime we have a terminal arm, we can start to sketch. Let's play around with another one. Let's say we're working with a terminal arm over here. Then we can start to play around with the related acute angles. And we could say, okay, so my related acute angle is either here or it's here, because I know it's always measured between my x-axis and my terminal arm. And then I ask myself, okay, which of these angles is acute? Which of these angles is the smaller angle? That's the one I'm going to be working with here. So in this case, my related acute angle would be measured on the right-hand side because of the quadrant in which I'm working. Now, a coterminal angle, this is the last of some review terminology. A coterminal angle shares the same terminal arm as another angle. So in this case, if we're working with angle theta as our as our principal angle, then a coterminal angle would be what we sketched before, going all the way around and then ending up at this same location. If this is the case, if we're working here, we'll call it theta 2. Then theta 2 would be equal to 2 pi, because 2 pi is all the way around the circle. So 2 pi plus an angle from here to my terminal arm. And we already have an angle there, so hang on, let's piece this together. So that's 2 pi plus an angle from my positive x-axis to my terminal arm. I already have an angle in there. That is angle theta. So angle theta and angle theta 2 would be what we call coterminal angles. All right, these are two angles that share the same terminal arm when we measure them. in standard position. All right, now all of this so far should be review. The only additional spin on it is now we're working with 2 pi instead of 360 degrees here for our coterminal angle. And we're working obviously with pi over 2 instead of 90 degrees that you would have been working with before this course. Now we're going to push on forward and we're going to work with 7 pi over 3 and negative 5 pi over 6. First we'll work with 7 pi over 3. Okay, so 7 pi over 3. If I'm drawing this in standard position, that means I'm drawing from the positive x-axis. If you have an idea on how to sketch this, maybe pause the video and try it out. But if you're not sure, watch along with us. Now, 7 pi over 3, I need to ask myself, okay, well, I know that 0 radians is here. I know that pi over 2 is up here. I know that pi radians are over here. And 3 pi over 2 are down there. Okay, so I need to ask myself, where does 7 pi over 3 lie in these? Well, 7 pi over 3, I know that's greater than pi. So I know I'm at least going to have to go that way around. And then I'll ask myself, okay, is 7 pi over 3 greater than 2 pi? Yes, it is, because 2 pi, remember, is 6 pi over 3. So it's still greater than 2 pi. So then we need to go all the way around again. And then we have what's remaining is pi, right? Because if I'm counting up my pi over 3s here, then I can go along and I can say, okay, pi over 3 would fall in this quadrant. 2 pi over 3 over here. 3 pi over 3 is along here. 4 pi over 3, 5 pi over 3, 6 pi over 3 is 2 pi. And then we look and we say, okay, so 1 more pi over 3, we're working again with this same terminal arm. So if I'm drawing this angle, what I've learned is I need to go all the way around once, and then I need to go from my positive x-axis all the way up to what kind of an angle here? Well, this was our pi over 3 angle, right? So it shares the same terminal arm as pi over 3. I'm working here, this angle, theta is equal to, and you know what, we'll just label this as 7 pi over 3. Now, that's great. It's sketched in standard position. If we can come up with the principal angle, we need to make sure that the angle we're working with, has to be positive, and it has to be between 0 and 2 pi. Now, where we started, 7 pi over 3, is that positive? Yes, it is. Is it in between 0 and 2 pi? No, it's not. It's greater than 2 pi, as we can see from our sketch. So if we're measuring our principal angle, we always start at our positive x-axis, we go all the way up, and there we are, our principal angle we already found. Our principal angle is pi over 3. We'll call that angle theta. All right, then we're going to work with our related acute angle. The related acute angle, remember, the related acute angle is from my terminal arm to my closest x-axis. So my two options, from this terminal arm, I can get to my x-axis by going to the right or by going to the left, and that is by going clockwise or by going counterclockwise. Now I need to choose the smallest related acute angle. So I'm not looking over here. This is not an acute angle. This is an obtuse angle. This is greater than pi over 2. So I need to work on this side. My related acute angle, always positive. Right here is the angle in between my positive x-axis, in this case, and my terminal arm. So in this particular case, my related acute angle, you notice, is equal to my principal angle. That will not be the case every single time. Now, if we're coming up with a coterminal angle, we'll go with a nice blue color. If we're coming up with a coterminal angle, then we need to come up with another angle that shares this same terminal arm. We could go with pi over 3, because pi over 3 is another angle compared to 7 pi over 3, but we'll play around with this and we'll see our options. We could go around the full circle once, and then we could go around the full circle again, and then we could head up to our terminal arm, in which case we would be working with 2 pi for going around, we'll call this theta 2. 2 pi for going around the full circle once, plus 2 pi for going around the full circle again, plus the pi over 3 that's needed to get to our terminal arm. If that's the case, we're working here and we have 6 pi over 3 plus 6 pi over 3 plus pi over 3. Okay, so 6 plus 1, that's 13 pi over 3. And that's great. That's one option for a coterminal angle here. Can we come up with another? Absolutely. Let's work here, and I'll try and clean this up a bit. Now our coterminal angle, there's nothing that says our coterminal angle has to be counterclockwise. So we could measure it here. If we're going in a counterclockwise direction, we just need to make sure we're working with negative values. So we head around here counterclockwise, we go pi radians around, and then we go another certain amount over here. How much is this? Well, we can come up with this pretty easily, because I could see if I add this blue angle here to this orange angle up here, they would make a full circle. And if they make a full circle, that's 2 pi. So here, my theta 2 is going to be equal to 2 pi minus this related acute angle, pi over 3. So this coterminal angle, whoops, and sorry, I forgot we already called one theta 2. We'll call this theta 3. It's going to be equal to 6 pi over 6 minus pi over, whoops, 6 pi over 3 minus pi over 3. And that is, we're working with negative 5 pi over 3. And bear with me here while I fix up my signs here, because bear with me here. I wish I had the chance to edit that out, but I won't, and that's okay. I should be working with an always positive related acute angle and a negative 6 pi over 3 right here, because we were going in a counterclockwise direction with my blue line. Fantastic. So that's great. You should be able to handle. Try it out. Try sketching negative 5 pi over 6 over here. Try coming up with a principal angle, a related acute angle, and a coterminal angle for this. I'll say try it out. Pause the video, try it out, and then come back here. We'll take up a little bit of it. Absolutely. Okay, so we're working with negative 5 pi over 6. Now, if we're working with negative 5 pi over 6, the first thing that stands out is negative 5 pi over 6 is a negative angle. And if it's a negative angle, that means we're still measuring from the positive x-axis, but that means we're measuring in a counterclockwise direction. We're going to go counterclockwise by 5 pi over 6. So we ask ourselves, okay, we know if we're going in a counterclockwise direction, this angle down here would be negative pi over 2. This angle up here would be negative pi. And if that's the case, I need to ask myself, I need to look at this here, and I can say, okay, well, 5 pi over 6 falls between pi over 2 and pi. So negative 5 pi over 6 will fall in between negative pi over 2 and negative pi. And if you're unsure of that, remember what pi means is half a circle. So instead, if we're working in units of half a circle, this is negative 5 over 6 half circles. Okay, well, negative 5 over 6 half circles, that's going to be more than or rather, that's going to be a further distance than negative half of a half circle, and it's not quite going to be all the way around. So we're working here, and we should have something like this. And we know right here how much distance is in between these. We'll find that in a moment. So this means, okay, we're working here. This angle that we found, this is negative 5 pi over 6. Good job. Now we're going to look at our principal angle. Well, my principal angle, remember, is always measured in a clockwise direction from my positive x-axis. So that means I'm working here, and I'm going halfway around the circle here. Halfway around, that's pi radians. And then I'm going another little distance here. Well, what is that distance? Well, I know together, in this case, together, my principal angle plus my angle negative 5 pi over 6 together would equal 2 pi. They would create a full circle around. So that means where I'm working right here, 2 pi minus 5 pi over 6, and that's really, I'm adding negative 5 pi over 6, is going to be equal to my theta, my principal angle. So my principal angle here, that is pi is equal to 2 pi, theta is equal to 2 pi. Now 2 pi is 12 pi over 6 minus 5 pi over 6. Okay, 12 minus 5 I'm working with 7 pi over 6. That is my principal angle right here, 7 pi over 6. Okay, that's great. Now where I'm looking is for my related acute angle. My related acute angle, remember, is measured in between my terminal arm and the closest x-axis. I'm going to sketch out both options here, and we can see very quickly the smaller option, that's going to be the closer option to the x-axis. That's what we'll be working with here. So my related acute angle is the distance in between this x-axis this time, that's my negative x-axis, and my terminal arm. Well, my negative x-axis, it depends on which direction I'm working here. I could say, okay, well this I know is negative 5 pi over 6, but all the way around would have been negative pi. So that means what's left in between? Well, that's pi over 6. If I'm working in the other direction, I can say, okay, well, I go around by pi units, and then I have to go around a little bit more, and it's that little bit more that I'm looking for. How much is that? Well, if I go around by pi, and I still have one more pi over 6, then what I'm working with is pi over 6. That's my related acute angle. If we're labeling it, we should always label it with alpha. Did I do that last time? Yes, I did. A coterminal angle, there are an infinite number of options we can use here for the coterminal angle. You could go with just the principal angle here if you want. You could go by going counterclockwise around a full time and then hitting the hitting the terminal arm. Play around with it, try it out, come up with your own coterminal angle. All right, then we're going to get into some special triangles. Now, special triangles are a great example for us to play around with because special triangles are something that perhaps you would have spent some time memorizing in grade 11. But memorizing is not the approach we're going to use in here. And that's because we're going to look for a little bit more understanding. We want to memorize, rather than memorizing what the triangle looks like, we want to memorize how to build these special triangles. Now, I'm sure some of you remember a little bit of how these special triangles are put together. So let's work right here. We'll come up with our first special triangle. You would have heard this referred to as the 45-45 special triangle, or you would have heard this referred to as the, now we could refer to it as the pi over 4 special triangle. Now we'll come up with it, let me see here. We'll jump right in and we'll use our radians because we should be able to handle our special triangle with radians here. All right, so we're working here. We start off, and you know what, I'll use another color there. We start off with this special triangle with 2 lines, each of which are 1 unit. That's the start of our work here, and the rest of our entire work is going to be accomplished through analysis. So here, okay, if we have 2 lines, we need to make sure we come up with a third line to create a triangle. For this triangle here, we have a 90-degree angle between these 2 1-unit length lines. Now, if that's the case, we should be able to come up with the length of the third line. How can we come up with the length of the third line? Using our Pythagorean theorem. You have been using that for years. So the length of this third line, remember this is the hypotenuse, it's directly opposite our right angle. The length of this third line, okay, we need to use a squared plus b squared equals c squared. The hypotenuse, that's c, is going to be equal to the length of the other 2 sides, each individually squared and summed. So we're working here and we have 1 squared plus 1 squared is equal to c squared, and that tells me that c squared is going to be equal to 1 squared. That's 1 plus 1, so 2 is equal to 2, meaning c is equal to the square root of 2. Now, really, you folks have learned this. If we're going to take the square root, we need to take the positive and negative options. There's no such thing as a negative length here, so we can kind of skip that step, or rather we can do that step and realize we're going to need to play with the positive square root here. So we're working with c is equal to the square root of 2. Great job. That's the first step in our analysis. Now, since each of these side lengths is side length 1, then there's a little bit of symmetry to this triangle, right? If I head along the triangle in this direction or in this direction, I'm going around the exact same angle inside because each of these side lengths are the exact same distance. Okay, well, if each of these side lengths is the exact same distance, we can take advantage of a rule that you have come across before. Okay, well, we know the sum of all interior angles is the sum of interior angles is 180 degrees. That's great. That's what you would have said in grade 11, but now that we're in grade 12, we don't say 180 degrees. We say pi radians. The sum of interior angles is pi. Okay, well, that's great. This angle right here, this is a 90-degree angle. Whoops, no, wait, we're in grade 12. So this is a pi over 2 angle. So if this is a pi over 2 angle, and these two interior angles are equivalent, are the same, then we can come up with it here. Okay, so the sum of interior angles, we're working with, it has to add up to pi, and we know one of these angles is pi over 2. So then we can call them angle, I don't know, we can call them angle A plus angle B right in here. We can call this angle A and angle B plus pi over 2 is equal to pi. Okay, so that means pi minus pi over 2, and that is pi over 2, is equal to A plus B. And since we know A and B are the same angle, we can skip a bit of a step in the analysis here. We're working, and B must be equal to pi over 4. A must be equal to pi over 4. And we're working here. We have now derived the entirety of this special triangle. Now, we will use this special triangle in the future. We don't need to practice using it quite yet. We'll leave that for the second half of the lesson. All right, now that's one of our special triangles. What I would like you to do now, stare at the screen. Try to think of the process we just went through. The first step was starting with two lines, 1 unit each, meeting at a pi over 2 angle, meeting at a right angle. Our second step was to use our Pythagorean theorem to come up with the third side length. And our third step was to use the sum of interior angles to come up with those interior pi over 4 angles. Great job, us. Okay, well, that's one of our special triangles. We'll go through one more. Now, where we start with the next one is we start with an equilateral triangle. And you know what? I'm just going to move this material over just a little bit to give us a bit more space. Fantastic. I know you don't have that freedom, and I apologize. So we'll work here. We're starting with an equilateral triangle. So my equilateral triangle is going to look something like this. Now, our equilateral triangle is going to have side length 2 everywhere. Great job. That's the end of our starting position. All right, that's what we're starting with. The rest of our work is accomplished through analysis. Now here, if we have an equilateral triangle, that means it is that each side is equivalent to the other sides. That also means each interior angle is equivalent to the other interior angles. Now, if that's the case, we know we're working here. We know the sum of interior angles is equal to 180 degrees. Whoops, we're in grade 12. It's equal to pi radians. Okay, now if each interior angle is equivalent, that means we can split that pi up into 3 pieces. We're working with pi over 3 plus pi over 3 plus pi over 3 as our interior angles. Okay, great job, us. We have pi over 3 here. We have pi over 3 there. We have pi over 3 down here. Now, the next step, and I'm hoping actually you weren't working in pen here. The next step is to take our triangle and cut it in half. Cut it in half. Good. We're just going to work with half of this equilateral triangle. Now, if we're working with half of this equilateral triangle, that means we don't need one of the sides. So I'm going to get rid of this half. We don't need it. Okay, so that means I have a new triangle side down here. Now I have a right angle. My right angle, we know in grade 12, is measured by pi over 2. Okay, so now we need to make adjustments, right? This bottom side length is no longer length 2. It was cut directly in half. That means its new side length is length 1. Now we can use this angle as well. What happened to it? It was cut in half. What's half of pi over 3? Pi over 6. So that's our new, oops, I cut a little bit too far there with my eraser. We're working with pi over 6 up here. Pi over 6. Okay, now we could double check pi over 6 plus pi over 3 plus pi over 2. Does that equal pi? Try it out on your own. If you're trying it, great, maybe pause the video here. Now, then we need to look forward. Okay, do we have everything? No, we still have a little bit more work, right? We have all of the interior angles, but we only have 2 of the side lengths. We have a brand new side length here. How can we find this side length? Again, this is a right angle triangle. We can rely on our Pythagorean theorem. Okay, so a squared plus b squared equals c squared. Now, what side is this? We need to be really careful. This is not c, and that's the biggest trap here, is to say, okay, it's my unknown side, so I'm going to put it in there. But no, our c side, that's from our hypotenuse. Our hypotenuse is opposite to our right angle. Our hypotenuse here is 2. So this unknown side is either a or b. So we're working here, okay, so I'm working with 2 squared is going to be equal to, we'll call a1. So I'm working with 1 squared plus b squared. Try it out. Isolate for b. Pause the video, isolate for b. Unpause the video. The answer is coming up, after some elementary solving. We're working here, and we have b is going to be equal to plus or minus the square root of 3, and we know that as a side length, it needs to be positive, so we're working with plus the square root of 3. That is our third side length. So what I ask you to do here is pause the video in a moment. Pause the video, flip your page over, and practice sketching each of these special triangles. If you get stumped, rewind the video, head back there, solve it, and then practice it again until you feel comfortable with your ability to look down and sketch each of these special triangles by thinking them through. It's going to be way more useful to you to sketch these triangles by thinking them through, because that's going to be preventing mistakes in the future. Try it out. Pause the video here. All right, so at this point you should be able to sketch either special triangle basically on command. They are going to be a part of our solutions as we work through this entire chapter. You'll be earning marks, this chapter and the next chapter. You will be earning marks for sketching these as a part of your solution to justify your work. We'll already get a little bit of practice sketching these special triangles when we start as we continue in this note. Now, a little bit more of review here. So we're going to work, we have a triangle given here where our terminal arm it's actually labeled R for radius, and our terminal arm comes from the origin, comes up here. Now, inside this triangle, we have our principal angle. Here, our principal angle in this case would be equal to or related acute angle. Not necessarily required for this exercise, but is useful nonetheless. Now, if we're working here, if we have our angle theta inside, then our radius, like I said, is given by the terminal arm. That is, the length of this terminal arm would be our radius. Fantastic. Okay, now if this terminal arm goes towards this point, say, then this point, the coordinates would be given by x, y, where the x coordinate of this point, we can see along the x-axis here, is also the side length right beside this angle theta. This coordinate y is also given here. It is the side length opposite to the angle theta. This is the side length, the vertical side length, giving us the vertical coordinate of this point right up here. Now, we know we've been working with sine, cosine, and tangent for a number of years now. Sine, cosine, and tangent, these are our primary trigonometric ratios. Primary trigonometric ratios. Now, when you're working with these, I'm sure you will remember, we have a mnemonic device to help us remember. We're working with SOHCAHTOA. And this tells us that the sine, that's the S, of theta is going to be equal to the opposite side over the hypotenuse. Great, this is review. You started learning this in grade 9. You're using it again in grade 12. Fantastic. All right, our cosine, that's our C, is equal to the adjacent side over the hypotenuse. That's what the A and H stand for. Okay, adjacent side over the hypotenuse, leaving us with our tan, our tangent of theta, which is equal to the opposite side over the adjacent side. Now we can take this a little bit further. Those are our primary our primary trig ratios. Now we need to work with our reciprocal trig ratios. So the cosecant, that's what this stands for, the cosecant of theta is equal to 1 over the sine of theta. The secant of theta is equal to 1 over the cosine of theta. And the cotangent of theta, we're working with 1 over the tangent of theta. Just a quick little insight here. The most common mistake made working with your reciprocal ratios are to see the c at the beginning of cosecant and assume it's the ratio of cosine. And to see the s at the beginning of the secant ratio and to assume it's the reciprocal of sine. That's not the case. The letters just switch up. Why is that? Because mathematicians don't always make things easy. Okay, now let's say we're working with a special kind of circle. Let's say we're working with a circle with a radius of 1. I know you've worked with that before. That's your unit circle. Now, if you're working here with a unit circle has radius 1. If you're working specifically with a unit circle, then our radius is equal to 1. Good job. We'll come back to that. Okay, now our sine ratio. It's the opposite side over the hypotenuse. That's great, except we want to be able to write this in terms of x and y. Well, our opposite side to my angle theta is given by the coordinate y. That is, the side length is given by the coordinate of the point way up here. So we're working with the opposite side is y. Our hypotenuse, we can see, is r. Good, so we're working with y over r. That's the sine ratio. Okay, if that's the case, our cosine ratio, we're working with the adjacent side. So adjacent to this theta is side length x. All right, so we're working with x over r. Our tangent ratio, we're working with y over x. Now, if that's the case, I would like you to pause the video and fill out for your cosecant, your secant, and your cotangent ratios what those are in terms of x, y, and r. Try that out, pause the video, and when you come back, then you'll see all the answers at once. Good, so you're back. Well done. You should see that our reciprocal ratios are simply the reciprocal of the fraction that we had before. So what used to be, so if sine of theta is y over r, that means its reciprocal is r over y. If the cosecant of theta is x over r, that means its reciprocal is r over x. And if the tangent ratio is y over x, its reciprocal is x over y. Well done so far. Now let's go back to that special circle, our circle with the radius 1. If we're working with a circle of radius 1, then our sine ratio is actually equal to y over 1. Well, y over 1, that's just y. Okay, our cosine ratio, we're working with x. Our tangent ratio stays the same, y over x. All right, our cosecant ratio, if we're working with the unit circle, we're going to work with 1 over y. Our secant ratio, 1 over x. And our cotangent ratio, still x over y. These will come into play later. We will certainly be using these ratios. Now, remember, these orange ratios are only true if we're working with a unit circle. If the radius of the circle we're working with is 1. If our terminal arm has length 1. All right, we'll get into our last section of review here. Bear with me. I'm going to pause and plug my computer in. Fantastic. So here, we're going to look at our cast rule. Now, it's review. I know you learned your cast rule in grade 11. In grade 11, you explored the why of the cast rule. Why are the certain ratios positive in certain quadrants? We're not going to take time in this class to cover that because you've already learned it. If you're curious about it, I will be able to point you in a direction of a video, so just reach out and ask me. All right, so our cast rule. When we're working here, first of all, we're working with the 4 quadrants. We haven't played around yet. We have not reviewed how these quadrants are labeled. These quadrants are labeled numbered 1 through 4. Now, they're labeled always using Roman numerals. Top right, the positive, where x is positive, and where y is positive, in this top right, in this top right quadrant, you may have heard Sadie the puppy tossing her food bowl around right there, asking for some more food. Now, quadrant 1, top right, we label them with Roman numerals. Quadrant 2, we label them in the counterclockwise direction, the same direction in which we measure our angles. Quadrant 3, bottom left, and quadrant 4, bottom right. So in these quadrants, we work with what we call our cast rule. Now, our cast rule tells us that in quadrant 4, we always start bottom right and then we go counterclockwise with our cast rule. Tells us that our cosine ratio will be positive here. Cosine of theta is positive. Now that means the other two ratios, our sine ratio, the sine of theta, and the tangent ratio, the tangent of theta, will be negative ratios if we're working in this quadrant. Now that also means we can take this a little bit further. If the cosine ratio is positive, that means 1 divided by the cosine ratio, its reciprocal ratio will also be positive. So if a primary trig ratio is positive, that means its reciprocal ratio will also be positive. Okay, then we have the A in cast. A means all the ratios are positive. So if all the ratios are positive, sine, cosine, and tangent, all of them, we're working with positive values. S, our sine ratio is positive in quadrant 2, and in quadrant 3, we're working with T, our tangent ratio is positive. So you'll see that in play here as we work through example 2. We'll see, we might end the video here after example 2. We've practiced it a little bit, and then continue the video for Thursday's class. All right, so example 2, we're going to state the primary and reciprocal trig ratios for this angle. Now you have actually solved a problem like this in grade 11, but obviously it looked different because you were working in grade 11 with angles in degrees. These angle measures were working obviously with radians. Now we have a bit of a procedure here on the right hand side. We'll want to follow it if we're going to come up with our ratios. So we'll start off. Number 1, we want to sketch the angle. Well, we know how to sketch the angle. We sketch this angle in standard position. And we sketch this angle. That means we sketch this angle. We want this in a counterclockwise direction measured from the positive x-axis. Great, except this angle is negative. So if it's negative, that means we measure it in a clockwise direction from, again, the positive x-axis. Now, so if it's negative, we're measuring, okay, so it's pi over 6. Now, pi over 6 should fall right here. Remember, pi over 6, if you're struggling there, whoops, negative pi over 6. Pi over 6, if you're struggling, you can refer back to our lesson in 6.1 if you're not sure how we know it falls into this quadrant. Good, so we've sketched our angle. Good job, us. The next step is to state our angle alpha. Remember, our angle alpha, that is our related acute angle. And bear with me here, folks, we've stopped responding. And we're back. Hopefully this is a long recording, and I'm really hoping it all lines up. So our related acute angle, that's angle alpha. All right, now we measure this from our terminal arm to the closest x-axis. That means either to the positive x-axis or to the negative x-axis. Here we can see the closest x-axis. That's our positive one. So we're working right here. The related acute angle is always positive. So it's the distance, it's the angular distance in between the terminal arm and the positive x-axis. We're working here. If we measured negative pi over 6 to get here, then we know our related acute angle is a positive pi over 6. Good job, us. All right, now what we need, we've found this related acute angle. Now what we need to do is find the special triangle that goes along with this related acute angle. So that means we need to sketch a special triangle that includes the angle pi over 6. I'll encourage you to pause the video here, come up with that special triangle on your own. You should be able to do that because you practiced it earlier. All right, so we'll take that up right here. It's sketching the special triangle. We know we're working. We start off with an equilateral triangle. We know each side length is 2. Good job. That's great, except it has to get cut in half. We're only looking at the right-hand side here, so our bottom side length is no longer 2. It's side length 1. We know from our Pythagorean theorem that we're going to work with the square root of 3 right here, and that is 2 squared, that's 4, minus 1, the square root of 3. Okay, now we know this was an angle on my original equilateral triangle, that is pi over 3. We know this was an angle on the equilateral triangle, but it got cut in half, so it's no longer pi over 3, it's pi over 6. That's the special triangle you need to show. You don't need to show all of the algebra analyzing this triangle to come up with it, but this is a part of your solution. If you try and answer this question without sketching this special triangle, you will not earn full marks on an assessment. Alrighty, so we have this special triangle, good job us. Now we're going to double check with our cast rule. Okay, so our cast rule tells us that in quadrant 4, our cosine ratio is positive. It tells us, sorry folks for my funny zoom here, there we go. In quadrant 4, my cosine ratio is positive. Quadrant 1, all of them are positive. Quadrant 2, sine is positive. And in quadrant 3, my tangent ratio is positive. So I'm going to look here and I'm going to say, okay, my terminal arm, where does it lie? It lies in quadrant 4. So in quadrant 4, then my cosine ratio is positive. All of my other ratios are going to be negative. Great job. Oh my goodness, this zoom is driving me crazy. I apologize. I'm sure it's not that pleasant for your mind to work with here. Now, okay, so now we need to find those ratios. Remember, those ratios that we're working with, they ask us to find the primary and the reciprocal ratios for this angle. The primary ratios, those are the sine of theta, the cosine of theta, and the tangent of theta. So let's work first. We know the cosine ratio is going to be positive here. So if the cosine ratio is positive, where we're working here, we're saying, okay, our cosine ratio. Now we know cosine, that's, if it's going to be positive, sorry, bear with me here, then that means that this cosine ratio will be the same cosine ratio that we would have found if we were working with a, we'll call it a phantom terminal arm, in quadrant 1. So if we had the same related acute angle, but it was in quadrant 1, so if this is pi over 6 again in quadrant 1, then this ratio, this cosine of this phantom theta, would be equal to the cosine of negative pi over 6. So that means the cosine of pi over 6, bear with me here, and if you're a little bit lost, that's okay. The cosine of pi over 6 is going to be equal to the cosine of negative pi over 6. How do I know that? Because cosine is positive in both quadrants. If cosine is positive in both quadrants, we'll take advantage of the symmetry of these angles here, and we'll say, okay, so our cosine ratio is positive. That means the cosine of, and you know what, I'm just going to rewrite these down here. Instead of writing of theta, I'm going to write of negative pi over 6, because that's what I'm working with here. Cosine of negative pi over 6 and the tangent of negative pi over 6. Okay, so the cosine of negative pi over 6 is equal to the cosine of pi over 6. That's great. The cosine of pi over 6, I look here. Okay, I'm working with pi over 6. Cosine, that is, let's give ourselves a tiny bit more space. Cosine is adjacent over hypotenuse from SOHCAHTOA. Okay, so that's adjacent over hypotenuse. And if it's adjacent over hypotenuse, I'm working with my special triangle up above. And I'm saying, okay, the adjacent side, that's the square root of 3. My hypotenuse is 2. So my adjacent over hypotenuse is the square root of 3 divided by 2. So here, notice what we did. We used the related acute angle to restate my cosine ratio in terms of the related acute angle. I used my special triangle to interpret this ratio. I used my cast rule to know that cosine stayed positive when I was working with its related acute angle. Okay, so that means that's all well and great. Now I need to work with my sine and cosine ratios. Now my sine and tangent ratios. Now here, okay, so if I'm working with the sine of negative pi over 6, I know if I'm in quadrant 4, then my sine ratio will be negative because cosine is the only positive ratio here. I apologize. Here we are. We're in the right spot. So that means I'm working here, and my sine ratio is going to be negative. So I'm working with negative the sine of my related acute angle, that is pi over 6. Okay, well, that means I'm working with negative, and then I can find the sine ratio of pi over 6 using my special triangle. So I have pi over 6 here. Sine, that's opposite over hypotenuse, so that's 1 over 2. That's negative 1 over 2. That's what I'm working with right here. Okay, good job us. Now let's work with our tangent ratio of this pi over 6, except I'm working with the negative tangent ratio of pi over 6. Why is it negative? Because of my cast rule. My cast rule tells me in this quadrant, my tangent ratio is negative. So my tangent ratio, okay, that's going to be my opposite over my hypotenuse. So that is 1 over the square root of, sorry, opposite over adjacent, 1 over the square root of 3. Equals negative 1 over the square root of 3. Why is it negative? Because it was negative on this line. I'm taking my negative tangent ratio. Those are my primary trigonometric ratios. You should be able to find as well your reciprocal trigonometric ratios. So we're working with the cosecant of negative pi over 6. We're working with the secant of negative pi over 6. And we're working with here the cotangent of negative pi over 6. Often the question that you're solving will not ask you to find every single ratio, but I'm hoping this extra practice can help you out. Now, remember, what is cosecant? Cosecant is the reciprocal of sine. If that's the case, we already found the value of our sine ratio. We're working here, okay, so it's 1 over the sine of negative pi over 6, and that is we're working with here 1 over negative 1 over 2. Okay, we know how to do that, negative 1 over 2. If we're working with the reciprocal here, that means we're working with negative 2. Fantastic. If you're confused about that a little bit, you can practice that by dividing it as fractions. 1 divided by negative 1 over 2, and that's 1 over 1 divided by negative 1 over 2, and that's 1 over 1 times 2 over negative 1. You're working with here negative 2. Good job, you. All right. Using that same logic, our secant ratio is going to be the reciprocal of our cosine ratio. All right, then I'm working with here nice and easy 2 over the square root of 3. My cotangent ratio is going to be the reciprocal of my tangent ratio. I'm working with here negative the square root of 3 divided by 1, and that is negative the square root of 3. Well done, folks. At this point, you know what? We'll practice one more. You know what? I think this video is getting long enough. You should be able to handle some of the practice problems at this point. We'll finish up the note on Thursday. Well done, folks.